Section 4.8 deals with the line of best fit. So the warm-up today asks to write the equation of a line in slope-intercept form that contains the points 1, 4, and 3, 8. This is an essential skill in being successful in Section 4.8. So we'll do this one together. So we have two ordered pairs, and we want to write an equation in slope-intercept form. So I need a slope and I need the y-intercept. So we want to start off by finding the slope. And in order to do that with two ordered pairs, we need to use our slope formula. Okay, so our slope formula says m equals y2 minus y1 over x2 minus x1. So I already labeled my ordered pairs, so I'm going to plug them in. So y2 is 8 minus y1 is 4 over x2 is 3 minus x1 is 1. When I simplify, I get 4 over 2, which means that our slope is 2. So we have the slope part of slope-intercept. Now I need to find the y-intercept. So the method that we're taking here is I've got an ordered pair and I've got a slope. So if I take my slope-intercept form and I write it, y equals mx plus b, I'm going to take x and y and m, plug it in to our formula, and solve for b. Then we'll have the slope and the y-intercept to then write our equation. So y is 4. Okay, remember I always take my first ordered pair. It's just easier to be consistent. So my y value is 4 equals my slope is 2 times the x value is 1 plus b. So if I clean this up, 2 times 1 is 2, so I have 4 equals 2 plus b, and to solve for b I need to subtract 2 from both sides. So that means my b value is also 2. So I have my slope, I now have my y-intercept, so I can plug in 2 for m, 2 for b, and then I have my equation of the line in slope-intercept form that contains these two ordered pairs. So my answer then is y equals mx, so 2x plus b, which is also 2. Okay, so a very, very good problem for the warm-up there, specific to today's lesson. So the goal is to be able to determine a line of best fit for a set of linear data. So we dealt with a line of best fit before where we would just draw the line of best fit from a scatter plot. But now we're going to specifically write a linear equation to represent that line of best fit. So the line of best fit, or our trend line, is the line that comes closest to all the points in the data set using a given process. So in order to write an equation of the line of best fit, we're going to draw a straight line. Okay, not a heart rate monitor chart. A straight line that best represents the data. Okay, it's going to generally go through the middle of the points, where some points are going to be slightly above and some points will be slightly below. We need to find two distinct points on the line, which will then allow us to find the slope. So we're going to calculate the slope of our line using those 2 points and our slope formula, which we used up here, y2 minus y1 over x2 minus x1. Now here's where things can kind of vary. If our graph has a very clear, distinct y-intercept, we can go straight to slope-intercept form. However, if it doesn't have a y-intercept, we can either use point-slope form, or we can use slope and one of the ordered pairs to then solve for b, just like we did up here, to write our equation in slope-intercept form. Okay, so we might have some variance here with the last couple steps. So we have 3 examples in this lesson. The first one says the graph below displays the height and weight of several students. We want to find the equation for the line of best fit, describe the correlation, and determine how much we would expect a student to weigh if they are 160 centimeters tall. So this particular scatter plot and trend line, it's already done for us. So what we want to do is we want to make sure we take a look at our X and Y axes labels. You look at your X and Y scales. What are we counting by on the X and Y axis? You'll notice we've got these little squiggly markings here. So this just simply means it's a break in the graph, and we addressed this earlier, where it means that from 0 to 134 on the X, we're not going by the same scale as all of the other X tick marks, as I call them. Okay, so all the other X's in between these numbers, technically it's each little grid line is 1. So 134, 135, 136, 137, 138. But because there were no data values from 0 to 134, they just kind of cut that part off so that it's not just in the way and making the graph bigger than it needs to be. And then the same thing with the weight. Okay, so on the y-axis, each tick mark or grid line is 2 kilograms. Okay, but we jumped from 0 to 30 right off the bat, so we had a break in the graph. So if we follow our process, we need to, the straight line is already drawn for us. Notice we've got about half the points above, about half the points below, and we're generally following the flow of the data. Okay, so part 2, step 2, says find 2 distinct points on our line. So let's pick 2 perfect points, as I like to refer to them. So this point right here, to me, is perfect. It's right on the crosshairs, where X is 148 and Y is 52, so that one jumped out to me. And then this one, and again, you might find some other ones, especially depending on when you draw your own lines. Your points may vary. This one is also really nice when I look at it. So X is 138, Y is 36. So let's write down our ordered pairs. So I always kind of go left to right. So my first ordered pair is going to be 138, 36. So that's X1 and Y1. And my second ordered pair is 148 and 52. So that's X2 and Y2. Okay, so step 2 is now done. We found 2 perfect points. Now we're going to calculate our slope using the slope formula. So my slope formula is m equals y2 minus y1 over x2 minus x1. Plugging in, y2 is 52 minus y1 is 36 over x2 is 148 minus x1 is 138. Okay, and again, because this is a word type of problem, a real life situation, a decimal representation for the slope would be appropriate. Okay, so if I do 52 minus 36, that's going to give us 16. Oops, don't want my calendar. So that's 16 over 10, which is 1.6 for my slope. Now, if I think about what that slope means, okay, again, slope is change in y over change in x. 1.6, an increase of 1.6 kilograms per centimeter. Okay, y over x. 1.6 kilograms per centimeter. So there is our slope, and now we need to write an equation. Okay, now it says if your graph has a y-intercept. This graph does not have a y-intercept because of the break in the graph. So what we're going to do is we're going to write an equation, okay, and we're going to put it in slope-intercept form eventually. Okay, so right now I've got slope and I have an ordered pair because we just love that slope-intercept form. So if I start off with y equals mx plus b, I'm going to put 36 in for y equals m is 1.6 times x, which is 138, plus our unknown yet is b. So if I do my 1.6 times 138, that leaves me with 36 equals 220.8 plus b. Now I would subtract 220.8 from both sides, and for the sake of saving space, I'm just going to write that result, that my b value then is negative 184.8. Okay, so because we love slope-intercept form so much, we'll write our equation in slope-intercept form. You're not tied to it because it does say just write an equation, so we could technically do point-slope form, but slope-intercept usually is a little more friendly and gives us a little more meaning. So if I go back to y equals mx plus b, we're plugging in m and b now, leaving our y and x as y and x. So y equals m is 1.6 x minus 184.8. Okay, so there is our equation to represent our line of best fit. Okay, the one thing this graph is missing is a title. Okay, so this would be student data, height and weight of students, whatever. Now, in terms of correlation, what's happening? Is it positive correlation, negative correlation, no correlation? Well, as we go from left to right, this graph is increasing. So this is going to be positive correlation. And let's describe that in a little more detail. So let me get my text box here. We're going to use the x and y axes labels to describe the scenario. So this is positive correlation. So remember, when we're describing correlation beyond just using positive, negative, no correlation, we talk about as x increases, what's happening to y. So as x increases, y is also increasing. Well, what does x represent? What does y represent? So as the height of a student increases, which is the x, the weight of the student, which is y, also increases. Okay, it doesn't need to be anything real fancy or flowery. Okay, describe as x is going, as x is increasing, what's happening to the y. Is it going up? Is it going down? And just use the labels. Okay. Now, part C is asking how much would you expect a student to weigh if they are 160 centimeters tall? So we're going to use the information on our graph and determine, okay, 160 represents what? 160 centimeters is an x value. So I'm going to take my 160 and I'm going to plug it in for x, and then I'm going to find y. Okay, so this is x. And in a perfect world, we would have written a let statement. So let x, we'll do that now, equal x was height in centimeters. So we're taking 160, plugging it in for x, and we'll do the plug and chug. So y equals 1.6 times 160 minus 184.8. So 1.6 times 160 is 256. So y equals 256 minus 184.8. And when we do that, we have y equals 71.2. And that's a y value, so that's going to be kilograms. But we should technically write a quick sentence. Okay, so a student who is 160 centimeters tall would weigh approximately 71.2 kilograms.
Here's what I found.
Whoops. Guess my watch is listening. Okay, so a student who is 160 centimeters tall would weigh approximately 71.2 kilograms. Now, if we look at our graph, okay, and we go to 160 on the x, notice kind of, we didn't go that far out. So if we were to extend it, we could kind of verify, but we're getting more exact answers now that we have literal equations. Okay, so let's take a look at number 2. Number 2 says the table shows the age of a car in years and its value in thousands of dollars. Use the data to construct a scatter plot and draw a line of best fit. We're then going to find an equation for the line of best fit, interpret the meaning of the slope and the y-intercept. Okay, so got our data values, so let's plot those. Now notice the coordinate plane is kind of already set up for you. We've got x represents the age of car in years. So the x-axis is counting by 1. The y-axis represents the dollar value in thousands for our car. And the overall scenario is talking about value of a car over time. So we need to make sure we put that. Value of a car over time. Oops. All right, so I'm going to plot my ordered pairs here. So a car 1 year old has a value of approximately $24,000. So on the y-axis, if we go 0, skip 1, 5, each of the intervals here is technically 2.5 or 2,500. So at x of 1, y needs to be about 24. So here I would be at 22.5. We're going to be a little closer to 25 than 22.5 there. So we'll plot that. Next at 2, when x is 2, y is 21. So 2, this is 20. This would be 22.5, so we're going to be a little bit under the halfway point there. Next we've got 3, 19, so x is 3. Here we've got 20. This would be 17.5, so we're going to be a little bit more than half there. 4, 18 is our next ordered pair, so 4, and then we're going to be just above the 17.5 line. 5, 15, that's a nice one. 6, 12, so 6. Here's 10, this would be 12.5, so just below the 12.5. 7, 8, so x is 7. Here we've got 10, 5, 7.5, so just above 7.5 would be approximately 8. And then we've got 8, 7. So 8, here's 7.5, so just below the 7.5. Okay, so you want to be very, very precise as possible when you are approximating these ordered pairs. Now we need to draw a line of best fit. This could take multiple attempts. Okay, we want to make sure that we're following the general flow of our data. Okay, and some points are going to be above, some points are going to be below. So I'm going to try to kind of, oops, that's not even the right tool. Let's make a straight line. That would help. Make it a little bit bigger. So I'm going to try this one. Not in love with that. I don't hate it, but I don't love it. Primarily because I have 1, 2 points underneath and it looks like 4 points above, so I'm going to adjust. Now this is where you guys have an advantage over me. You can just move your rulers before you draw your line, so I'm kind of adjusting, all right? So this to me looks a little bit better. Okay, I've got 2 points definitely below the line. I've got 2 points definitely above, a couple that are touching, so I'm going to draw it there. Okay, so I'm following the general trend of the data. Notice how I extended, okay, to the left and to the right. Just make that nice big line. Okay, so pretty accurate. I like this one. So that's a decent line of best fit, or trend line, but now we have to write the equation for the trend line, which is technically our line of best fit. So we need to find, step one was draw the straight line that generally represents the flow of the data. Now we need to find 2 distinct points. Now, not necessarily distinct points that were on our table, okay, which we kind of hit a couple of them, but we can look for perfect points as well. Okay, so looking at our grid marks, I mean, I've got 2 points right here that are relatively perfect. Not perfect, but close. So I'm going to do 2 perfect points, one that's perfect for grid marks on the background, and one that's perfect-ish for the table. So my 2 perfect points I'm going to use this one right here, which is where I cross the y-axis. It's really close to what would be 27.5. I could even call that 27 if I wanted to. And then another perfect-ish point, we could either go with this one, we're touching that one, we're touching this one. Let's go with this point down here. So that was our last ordered pair. That one was a point from the table. So that was 8, 7. So I'm going to use this one too. And depending on your line, your points, you may have slightly different points, but we should ultimately be in the ballpark at the end once we actually find our slope. Okay, so we're going to go ahead and I'm going to write 2 perfect points. And I'm going to go ahead and I'm going to call that 27 instead of 27.5. So I'm just going to kind of point this out as the x value is 0, and I'm going to call that y value 27. And let me flip my screen back around so I can write neatly. And because this x is 0, that means I actually have a y-intercept there. That's my y-intercept, so that's going to help me out a little bit later on. Okay, so that's a perfect point from the grid lines, and here's a perfect-ish point from the table, which was 8, 7. And I'm going to label x1, y1, x2, y2. All right, so our slope formula is y2 minus y1 over x2 minus x1. So our y2 is 7 minus our y1 is 27 over x2 is 8 minus x1 is 0. So that's going to give us negative 20 over 8. And again, we've got a real life situation here. So when I do 20 divided by 8, that's going to give me negative 2.5. So my m is negative 2.5. Okay, so I've got slope. If I'm going to go slope-intercept form, I need the slope and I need the y-intercept. And I do have the y-intercept. Okay, it's right here. Let's label that. Okay, so because we cross through the y-axis and there's no break in the graph or anything, it means our b value, based off of our approximation here, is 27. So if I write my y equals mx plus b, I now have very little work to do. I just need to plug in negative 2.5 for M and 27 for B. So y equals negative 2.5 times x plus 27. Now, before we get too far, what does our x represent? Well, x, we don't have to use much in terms of context clues. We've got a table here. X represents the age of a car in years. Okay, so right there, let x equal age of car in years. And remember, we do have to be very careful in that the y value is talking about the value of the car in thousands. Okay, so let's now interpret the meaning of the slope and the y-intercept. Again, slope, change in y over change in x. So if I just take that decimal version of the slope and I write it as kind of a fraction, we force that, write it over 1, change in y over change in x. Y represents the dollar value, okay, in thousands. So dollars in thousands over the x value represents age in years. So down $2,500 every 1 year is what our slope represents. Okay, and we didn't need to just pull that out of left field. Okay, use that delta y, change in y over change in x, rise over run. Use those labels to your advantage. Okay, so m, which is negative 2.5, means the value of the car goes down $2,500, right? 2.5 thousand would be $2,500 every year. And the y-intercept, well, that represents when x is 0, y is 27. When the age is 0, the value is 27,000. Okay, so this car, the price or the initial price of the car is $27,000. Okay, so B of 27 means the initial price of the car was $27,000. Okay, very, 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 very important. Oops. Okay, and we will stop there for the moment.